All right, let's start chapter 21, alpha carbon chemistry. So we're going to first start off talking about what we mean by alpha carbon. So we're looking at the carbon that's directly connected to the carbon of our carbonyl. These are our alpha carbons. We can also use terms beta and gamma, as well as delta, to describe carbons and their proximity to the carbon of the carbonyl. We specifically are going to be looking at the protons that are connected to our alpha carbons. From here on out, we'll call these alpha protons. Next, we need to establish the difference between an enol and an enolate. You can see that one difference is in the type of reactant that's used. To get the enol, we're going to find out that you need catalytic amounts of acid or base present, whereas the enolate formation is favored by a strong base. If you remember from Organic 1, we discussed the relationship between a ketone and an enol at equilibrium. Ketones and enols are tautomers of each other. Tautomers are rapidly interconverting constitutional isomers, differing in where the double bond and the proton are located. Remember that tautomers and resonance structures are two very different things. Tautomers are constitutional isomers. Resonance structures are not. Ketones and enols exist at equilibrium with one another. As shown here, equilibrium generally favors the ketone. In the next slide, we'll look at two exceptions to this. Here we're going to look at two exceptions where equilibrium will favor the enol. Anytime you have a 1,3-diketone, equilibrium will favor the enol. There are two reasons for this. Reason number one, the enol has a conjugated pi system, whereas the 1,3-diketone is an isolated alkene system. Reason number two, the enol has intramolecular hydrogen bonding. Both of these are stabilizing factors, which leads to the equilibrium favoring the enol. In this next example, we can see that equilibrium highly favors the formation of phenol and not the ketone. This is due to the fact that the ketone in this example lacks aromaticity. The phenol is much more stable because it is aromatic. Next, we're going to take a closer look at the tautomerization mechanism. The mechanism is going to differ by the order of either the protonation of the carbonyl oxygen or the deprotonation of the alpha position. These will just flip-flop based on whether we're under acidic conditions or basic conditions. Let's look at tautomerization under acidic conditions first. Protonation of the carbonyl oxygen will occur first. The electrons on the oxygen will go out and grab a proton from the acid source. Then this will form a resonance stabilized cation. The final step will reform our acid catalyst and deprotonate our alpha position, forming the enol. The base catalyzed tautomerization mechanism has the same steps except in the opposite order. The base will first deprotonate the alpha position, forming a resonance stabilized anion, followed by the protonation of the carbonyl oxygen to form the enol. Tautomerization is really difficult to prevent. It's always going to occur. You can just assume that there's always going to be small amounts of enol present whenever you have a ketone. Because of this, we need to look at the resonance structures that the enol can take on. This will help us understand the reactions that we look at later. Notice that the alpha carbon is actually nucleophilic. Okay, so it has electron density at this alpha position. This is going to be really important. So though this resonance structure of our enol isn't the major contributor to the resonance hybrid, it is very reactive because of this carbanion. Enols will generally form with catalytic amounts of acid or base present. However, if we are in the presence of a strong base, then an enolate is going to form. Enolates are much more nucleophilic than enols are, as it carries an overall negative charge. Let's identify the two nucleophilic sites on our enolate. It looks like we have a carbanion, that can be a nucleophile, and then the negative charge can also reside on the oxygen. Since enolates have two nucleophilic sites, the oxygen and the alpha carbon, we can get nucleophilic attack from either atom. Though the more stable resonance structure of the enolate results in oxygen attack, the resonance structure resulting in carbon nucleophilic attack is much, much more reactive. Hence, for the rest of the chapter, we'll be looking at reactions where the alpha carbon is the nucleophile. We will either see the alpha carbon attack drawn like this, originating from the carbanion itself, or drawn like this, where the carbon attack will originate from the most stable resonance structure. Both ways of drawing the carbon attack mechanism are equivalent. Ultimately, enolates are way more useful than enols in a reaction. Couple of reasons. Enolates possess a full negative charge, therefore they're much more reactive than enols are. Enolates can also be isolated or separated away from reactions as an intermediate, whereas enols cannot be separated. It's also important to mention that alpha protons are the only acidic protons on the aldehyde or ketone that can be removed to form an enolate. Therefore, our aldehyde proton, our beta or gamma protons are not acidic. For the reactions later in the chapter, it's really important that we choose an appropriate base for the enolate formation. Looking at the reaction on the right side of the screen, you'll notice that the pKa values of both the reactant and the product, the acid and the conjugate acid, are really similar. So what this means is that both the product and reactants will be present in significant amounts. When the alkoxide is used, the enolate, which is a nucleophile, can react with the ketone and form a bond. Sometimes this is the desired reaction, but sometimes it's not. Sometimes we want to form an enolate completely and irreversibly, so we need to use a stronger base, such as sodium hydride. Remember, sodium hydride is just going to act as a base. It will not act as a nucleophile. So it will just be deprotonating our alpha carbon position to form the enolate. Another way to form enolates irreversibly is by reacting diisopropylamine with N-butyl lithium. This is going to form LDA, lithium diisopropyl amide. LDA has two bulky isopropyl groups attached to the nitrogen, which allows it to be a great base, a strong base, but not a good nucleophile due to the bulkiness. When protons are alpha to two carbonyl groups, they're much more acidic. This increased acidity is due to increased stability of the resulting enolate. Notice that the resulting enolate has resonance into both carbonyls. Therefore, 1,3-dicarbonyls are acidic enough to be irreversibly deprotonated by an alkoxide. You actually don't need to use sodium hydride or LDA to form the enolate of these 1,3-dicarbonyls. It would be overkill. So in the next few sections of this chapter, it will be important to know what base to use in order to generate the enolate. And it's going to depend on the carbonyl compound as well as the desired result. Okay, so whether or not you want to have a reversible enolate ketone reaction or one that's irreversible.